Hello, everyone. Welcome to our talk today on cancer detection versus non-contrast CT and deep learning. First, I'd like to introduce Dashu. Dashu is a 501c3 nonprofit organization. Our name is actually a pun in Chinese. Using the same pronunciation, Dashu, with one character written differently, it could either mean big data or big tree. There's a saying in Chinese that we plant a tree today for many future generations to enjoy the shade under its canopy. And what we aim to do is we aim to promote research and education in data science by creating a global community for people to learn, build connections, exchange ideas, and share opportunities. We have many activities that we host. We host frequent educational seminars and scientific conferences to promote learning and the knowledge sharing. And in doing so, we also help showcase the latest innovations and achievements from leaders around the world in their fields. We also offer training and tips for career development, and we provide opportunities for people to volunteer and help our community grow throughout the year. This is our current board and volunteers, so thank you so much for everyone who puts in effort to make all these events possible. And we need your help. We would welcome you to join this community so that we can become better together. Our membership is entirely free, and to join our mailing list for upcoming events notifications, please send an email to info@dashu.org. You can also check out all of our events notifications and previous events activities at www.dashu.org. Volunteers and donations are always welcome, and any donations that we receive are allocated according to a really strict financial system, and any administrative costs should be minimized to less than 3%. Any related documents and data that are collected, we collect thoroughly and we record comprehensively. So please consider making a donation and helping our community grow. We're also on LinkedIn, X, formerly Twitter, and WeChat under the name Dashu, and our YouTube channel holds the recordings of all of our previous talks and events, and we welcome you to check these out. Next, we would like to take some time to recognize our generous sponsor for this session, BeiGene. They're a global biotechnology company dedicated to discovering, developing, manufacturing, and commercializing innovative medicines to improve treatment outcomes and access for patients worldwide. With their patients at heart, BeiGene has 4 core values: patients first, collaborative spirit, bold ingenuity, and driving excellence. BeiGene's commitment to reducing the burden of drug development and costs aligns seamlessly with Dashu's mission, making them a valuable partner in our journey. BeiGene is committed to drastically reducing the burden of the cost of drug development by innovating towards 4 excellences: portfolio excellence, technology excellence, operational, and data excellence. And with data excellence as its foundation, the Data Science and Digital Innovations Team, DSDI, department within this Global Statistics and Data Sciences Department, GSDS, is leading a cross-departmental team to develop B1, which is a super app for drug development. B1 comprises independent business-driven data products built upon a clinical enterprise data acquisition repository to empower and accelerate business functional teams to derive real-time data insights and make data-driven decisions. Join BeiGene today to become part of their team that will make a difference for patients worldwide. For more information, please refer to their website for their career opportunities. Thank you for your time and listening to this. And we also want to announce that we're back with our Dashu Data Science Symposium, we're returning after a break due to the pandemic. Having hosted several successful symposiums pre-pandemic, we're eager to continue this tradition, and this year, the symposium will be held from May 16th to May 18th at Michigan State University in East Lansing, Michigan. Our theme is empowering medical insights with data and AI, super relevant to hot topics today, and it will feature several distinguished sessions, including in EHR and NLP, in imaging, genomics and biomarkers, drug discovery and development, and as well as workshops that cover emerging topics like large language models and single-cell informatics, all super relevant topics for today's science. We anticipate that the symposium will attract hundreds of visitors and researchers from both industry and academia, and we anticipate that there will also be vibrant discussions about these emerging opportunities and challenges in data-driven healthcare, drug discovery, and biomedical research. More details will follow in an upcoming email if you're subscribed to our mailing list, but please mark your calendars for May 16th to 18th, and we look forward to seeing you there. Next, I will introduce our introducer and one of our speakers for today, Dr. Li Lu. Li Lu is leads the global medical AI R&D efforts for Alibaba Damo Academy since August 2021. He previously also came to us with a talk in 2021, so we're really glad to have this opportunity to rehost some of him and his colleagues. And back then, he worked at PAI Inc., leading the division of Bethesda Research Lab after more than 5 productive years at the NIH Clinical Center, Radiology, and Imaging Science Department, and from the NVIDIA AI Infra Division, and after 6 years at the Siemens Corporate Research and the Siemens Medical Solutions USA corporations. He's an IEEE Fellow, which is a computer society on medical imaging, AI, and oncology since 2021, and also serves as as an associate editor for IEEE Trans Pattern Analysis and Machine Intelligence since 2019. He's also involved in the IEEE Signal Processing Letters and Frontiers in Oncology. In 2007, he received his PhD back then in computer science from JHU, Johns Hopkins University. Next is one of our speakers. He will be giving a talk on large-scale pancreatic cancer detection via non-contrast CT and deep learning. His name is Dr. Yingda Xia, and he's also a research scientist at Alibaba focused on real-world medical AI problems. He builds high-performance AI systems to detect cancer and advance that field. He received his PhD also from Johns Hopkins University and has published over 30 peer-reviewed articles in top AI and medicine-related conferences and journals, such as Nature Medicine, Nature Communication, and a couple more listed here. Within those conferences and journals, he has also had multiple oral and highlight appearances. Our second speaker for today, Dr. Jiawen Yao, he will be giving us a talk on effective opportunistic esophageal cancer screening using non-contrast CT imaging. And he also works at Alibaba as a senior algorithm expert. His current projects focus on developing algorithms for improving screening, diagnosis, and treatment recommendations in oncology for precision medicine. And he received his PhD from University of Texas at Arlington. He also has a impressive repository of over 50 published peer-reviewed journals in also top medicine-related conferences and journals, including some of these listed below, like Nature Medicine, Annals of Surgery, MICCAI, etc. And his work, Deep Prognosis, has been selected from the MICCAI Media Special Issue of Best Papers in 2020, which is quite an accomplishment. And another one of his papers is also one of the media's most cited articles. So super excited to welcome all of our speakers today. And I will hand it off to Dr. Li Lu for a quick introduction for their talks. All right.
Hello,
thank
everyone.
you.
Okay.
I will continue sharing this screen. There we go. Okay, go ahead.
Okay. Yeah, today I take thanks for inviting us here to share some of our recent development in non-contrast CT and AI for early cancer detection or screening. As we know, right now there's only like a 4 type of cancers has SOC standard of care screening protocols, like including like lung cancer, which is using low dose non-contrast CT. This line of work actually inspired by the daily work from clinical centers. So doctors or radiologists, they are responsible for all the incidental findings, like no matter what kind of purpose for imaging exam. Let's say for lung cancer screening, and you are not just responsible for lung nodules or other abnormalities inside the lung, you are also responsible for heart disease, any anomaly you can see. But non-contrast CT is not a very good protocol for human eyes. The CT has 12 bits, right? And our screen, our human eyes are mostly sensitive for 8 bits. So we have to, it's not native to our eyes to examine all the different anomalies, right? So why only CT screening protocol is available for lung cancer because lung cancer has about prevalent about 70 to 80 out of 100,000 people. So this considered as a relatively high frequency cancer. So the screening under this population is more beneficial than false alarms and other negative effects. And yeah, I just uh, take 3 minutes to discuss the general background. There's no slides. Yeah. So so it's very natural to detect everything using this non-contrastivity. There is a huge body of work, previous work from the literature, like this called incidental findings. So from a CT exam, from a CT scan, even a non-contrast CT scan, there are actually a lot of information, non-structured information in the scan like which need algorithm to consume to extract the clinical informations, especially for almost all the visible cancers, even some chronic disease. Like say from NLST dataset, you can estimate the CVD risk, a 10-year CVD risk, like heart disease risk, and you can estimate a lot of things, like maybe even the bone health. Yeah, there are a lot of things. We are currently working on using one CT scan. We can screening and quantitatively assessment of like A type of cancers and lymph node abnormality and also five type of chronic disease. So it's this we also another thing we commit to open science. If you pay attention to our publications in the leading technical conference and clinical conference like RSNA and like the leading clinical conference every year. We do publish, we do keep the open science, and you can actually see a lot of paper already in there indicating our work. So today, especially, I have two excellent colleagues. They are going to share their work on pancreatic cancer screening and also esophageal cancer screening. They can be well combined with like a CT scan, a lung CT scan, or chest CT scan, or abdomen CT scan. They are we have a very high level of performance compared to all the existing work. The bottom line is the CT contains a lot of information, maybe more than we think. So the high performance AI algorithm can really be utilized to really track this information almost for free because people do CT scan for various reasons. And we hope this tool, our automatic tool, can really be helpful for many of the patients. We already both of the algorithm are available from our cloud-based API. So we have been using this to serve already like hundreds of thousands of patients already in the screening population. Yeah. I think without further ado, I will let my colleague, like first Dr. Yingda Xia, to share his work. Then will be Jiawen Yao. Yeah. Thank you.
Okay, let me share my screen. 1 second, please. Okay, so thanks for Dashu and Dr. Lei Lu to invite me here. I'm here to introduce our recent work on pancreatic cancer detection using non-contrast CT scan. This work was recently published in Nature Medicine. Okay. First, I want to introduce some background of pancreatic cancer. The major pancreatic cancer is pancreatic ductal adenocarcinoma, in short PDAC, that is the solid malignancy worldwide, which has a 5-year survival rate of 10%. and most patients with PDAC are diagnosed at late stages. That's one of the reasons that account for the low survival rate. Currently, screening of PDAC holds the greatest promise to reduce PDAC-related mortality. And there's a recent study in JCO showing that pancreatic cancer surveillance can boost the survival of PDAC to 9.8 years. Basically, this is a 10-year study, so this is very impressive to boost the survival to 9.8 years. The current technique for pancreatic tumor, which unluckily cannot be used for screening purposes, are contrast enhanced CT, which is the most popular or most clinically used pancreatic tumor diagnosis protocol. There's also others for pancreatic tumor diagnosis, like endoscopic ultrasound, EUS, and MRI. Here, as Dr. Lu introduced in his introduction, we focus on non-contrast CT scans, which is widely used in physical examination centers and hospitals, mostly used in low resource regions where contrast agents are not that available. And the non-contrast CT only will have a lower radiation and free of contrast agent, which sometimes can cause allergic reaction of the patients or other side effects. We also have the fact that there are tens of millions of abdominal and chest non-contrast CT performed each year. Here, we not only focus on the abdominal CT, which covers the pancreatic region, we also focus on the chest non-contrast CT. This protocol can also cover a large part of the pancreatic region. And given this fact, can we use opportunistic screening, like incident findings, to find pancreatic cancer on this protocol? Another fact is it is very hard to detect and diagnose this pancreatic tumor on non-contrast CT, even for experienced radiologists. The contrast is very low, especially for early PDACs. We have research studies for non-contrast CT of radiologists using non-contrast CT only to detect early pancreatic cancer. I will show later. In this work, we want to use deep learning to solve this problem. Deep learning has shown expert level performance on various tasks in medical image analysis, such as breast mammogram or lung nodule detection. In some studies, the deep learning algorithm even outperform expert radiologists on some routine clinical tasks. So deep learning is very promising. We hope that AI-based opportunity screening can advance the early detection of PDAC on non-contrast CT. Here I want to introduce Panda, which is the name of our AI system, short for pancreatic cancer detection with AI. Panda can detect pancreatic lesion on non-contrast CT, including PDAC and 7 other non-PDAC subtypes, which are also tumors, actually 6 tumors plus chronic pancreatitis. Panda is trained on large-scale, well-annotated training data. In this study, we introduce a multi-center validation for the validation purposes, and also want to see if Panda can generalize to chest non-contrast CT, as mentioned before. We also focus and develop some novel evaluation protocols to see the clinical translation ability. I first go over the
Yingda, you may want to move closer to your computer, so your voice sometimes is too small.
Okay. Is this better or not? Better?
Yeah.
Okay. I move forward with to the microphone. Okay. The Panda development of Panda is showing this diagram. We train Panda using only the data from one internal center, which including over 3,000 cases. and the PDAC and non-PDAC lesions are confirmed by pathology. We also used the mask annotation transferred from a contrast enhanced CT, sorry, because directly annotation on the non-contrast CT is not say almost impossible, but it's very hard for even expert radiologists. So we have the radiologist annotate on the contrast enhanced CT first, then we transfer the annotation to non-contrast CT using registration. PANDA can detect and diagnose segment 8 types of pancreatic lesion. Basically, the model is a multitask framework which jointly segment and output the probability of the pancreatic tumor. I will go through the annotation process in detail here. We first collect the paired non-contrast and the contrast-enhanced CT for each patient, which is standard protocol in many hospitals, especially in China. The lesions are confirmed by pathology. Actually, all the patients underwent surgery, so this is surgical pathology here. And we have the automated annotation of pancreas. We have a line of previous works for pancreas segmentation, so this is not very hard to do in CT scans. And the radiologist annotate the tumor on the arterial phase, where they can see the tumors clearly. And we finally annotate the non-contrast image via the image restoration from the annotated mask from the arterial phase to the non-contrast phase. This is our model design. The PANDA is basically a 3-stage model. The first stage is for pancreas segmentation, which we use a simple NUNet network to segment the pancreas. Then we crop the ROI of the pancreas region to reduce the computation efficiency and also reduce the nuisance factors outside the pancreatic region. For stage 2, we use a multitask CAN where we jointly output the abnormality probability and also the pancreas and lesion segmentation. If we have a abnormal output for the stage 2, then we will go to the stage 3 to see the diagnosis, the differential diagnose which type of the tumor we have here. For stage 3, we have a dual path transformer, which we have a memory path and the image path. We do several cross attention here, and we finally output the probability of the specific type of tumor, including these 8 types as mentioned before. We also include the chronic pancreatitis here because chronic pancreatitis is sometimes sometimes confused with PDAC in clinical routine, so we include it here. We evaluate the model using these protocols. First, we have an internal test set, which includes hundreds of data. And then we have a multi-center external test set, which includes 9 centers here. And we have reader studies compare with the readers on non-contrast CT. We also want to compare the upper bound using the contrast enhanced CT, and we also see if PANDA can assist radiologists making decisions. We test the performance of PANDA to chest CT, and we also propose a new real-world multi-scenario study to see the clinical translation ability. Here is the multi-center validation. We have an AUC of 0.986 to 0.996 across 10 centers. Here, including internal centers, we have 1 internal center and 9 external centers. And the general sensitivity for stage 1 PDAC, the early stage PDAC, is 95 to 97 sensitivity. And we maintain a 99% specificity across the 10 centers. These are the specific diagram here, which I will not go over in detail. And to mention that we also have a non-inferiority to secondary radiology report in differential diagnosis, where the confusion matrix can be found here. We directly compare the differential diagnosis results of PANDA stage 3 of the 8 types of panda tumors and compare it to the second reader radiology report of a tertiary hospital in Shanghai, and we find non-inferiority for the accuracy. We also evaluate the interpretability of panda, which is important for AI models. If we want to interpret for the doctors, we visualize using GradCam, which is a very popular network visualization in computer vision. We visualize the features, intermediate features of the AI model, and we find the heat map correspond to the segmentation map of the PDAC, especially aligned with the radiologist annotation. We also evaluate the interpretability for differential diagnosis. Interestingly, we find that the attention, with self-attention in our stage 3 model, the attention of the model is in line with some interesting findings, which is related to the specific tumor type. For example, we have a chronic pancreatitis here. Chronic pancreatitis, when the radiologist make diagnosis, they will look at the calcification, they will look at the dilated duct, at the atrophy of the pancreatic tail. That's where the attention of our model is. And we also have another examples of MCN, another pancreatic tumor type. The attention region will be associated to the thick wall of the cyst and also the duct and the lesion relationship, which are also crucial to differential diagnosis, the different types of pancreatic cancer. Pancreatic tumor. The reader study shows that when compared to non-contrast CT, when radiologists read non-contrast CT, we have an average improvement, or we outperform the radiologist by about 15% sensitivity and 6% specificity on lesion detection, which means whether we can find a pancreatic tumor. And we also have a metric here over 30% sensitivity for PDAC identification, which means that if we can correctly identify a PDAC versus other types of tumor and normal patients. We also find Panda can assist readers making decisions on both lesion detection and PDAC identification. And we also test the Panda using non-contrast CT only to the upper bound. As mentioned before, the contrast enhanced CT, which is clinically used for the pancreatic tumor diagnosis. We have a slight outperform in lesion detection and a 10%, about 10% outperformance on sensitivity for PDAC identification. Here are some case studies. I basically show that these are really hard to find tumors with in the non-contrast CT, and even in contrast enhanced CT, the tumors cannot find easily. We can see that 15 readers on contrast CT, 12 out of 15 readers missed this small PDAC tumor. This is T1 stage, which is less than 2 centimeters in diameter, and Panda successfully predicting that. Here comes the generalization to chest CT. In this study, we also test the Panda on the chest CT because we know that there's tons of chest CT performed each year. And if we can associate this ability to the lung nodule screening, such as lung nodule screening, we can have numerous, maybe we can have numerous incidental findings for if we use Panda in the opportunity screening scenario. In this study, we collect the preoperative chest CT for validation. That means that if we have a patient who underwent surgery for pancreatic tumor, we check that if this patient had chest non-contrast CT before. If it is, within a certain period of time, we collect this and to run Panda on it. The AOC maintains 0.979. And the sensitivity is 86%. It has a sensitivity drop from our previous 95% to 86%. That's basically because in it can depends on the chastity protocol, but some pancreatic tumor are not fully scanned in the chastity because it's not scanned through the abdominal region. This is an illustration for it. If the lowest scan position is here, then the tumor is not scanned for pancreatic tumor. And if it's here, luckily we have that, then we hopefully we can find pancreatic tumor using our AI system. There's also interesting finding that even for those tumors that were not found, see, we have a lowest scanning position here, and the tumor is not scanned, then we don't have the tumor on the CT scan, we still has the chance to detect it. That is because the PDAC can sometimes cause a dilated duct. Duct dilation, which has a duct here. See, if the tumor is not scanned, but we have a duct dilated here, then Panda has a chance to detect this duct dilation and to make alarms to the doctors, say, oh, we don't find a tumor, but we find a dilated duct. You need to pay attention, something like that. So this is our last evaluation, is that we propose a real-world clinical evaluation. So what's the difference between the clinical evaluation than the previous retrospective study, the case control study, which is usually used in the academic papers, is that previous case control study is limited to pathology confirmed pancreatic lesions. We know that many pancreatic lesions are not usually surgically resected, and we want to see that if we can detect them. And the case control study, we cannot like collect 10,000 normal cases to test it. Usually we keep the positive negative ratio to 1 to 1 so that we have a balanced data set, and most academic studies will keep the number here. But if we want to use a opportunistic screening scenario, we need to test our system on a very large number of normal cases to see that if we generate a lot of false positive, right? So we come upon these critical questions for an AI system to be deployed in a real world scenario, and our evaluation is going to answer all these questions. The first is that what is the true performance in real world consecutive patients selected from different clinical scenarios? The second is that can Panda detect the misdetection of the standard of care? Can patient benefit from such detections? So if we detect a tumor that is very late stage, then this detection is not that useful, right? So can Panda also be clinically safe without false positives leading to unnecessary follow-ups? And can the benchtop derived AI be further improved according to bedside clinical requirements? That means that can the AI be iterated to satisfy the clinical needs, more clinical needs? We developed this clinical evaluation using 20,000 patients, 2 rounds. The first is 16,000 patients. The second is 4,000 patients collected from 4 clinical scenarios, which is physical examination centers, the emergency room, the outpatient department, and the inpatient department of a big hospital in Shanghai. And the timelines here, we collect this is also a retrospective study. This is not a prospective study. We also retrospectively collect these patients, but it's consecutive patients, span a month here. And during the Panda evaluation, something can happen, right? Some patients with follow-up when we collected, we see this is initial standard of care decision. And during this time interval, before the Panda was evaluated, some patients will have a follow-up standard of care decision. And here is the Panda evaluation. This is timeline. Let's see the problem, the performance of the real-world evaluation. Panda still maintains high sensitivity, about 85% tumor detection, and 99% specificity, and 50% PPV for PDAC identification, which means to identify the lesion is PDAC or is non-PDAC lesion or is a normal patient. Okay, this is more realistic in the cancer screening regimen. We have 95% sensitivity and 99.9% specificity and 56% PPV. We have PPV here because this is a consecutive patient. So we calculate this result. It's not a case control study. Okay. And inpatient had the highest sensitivity of 884.6, and physical examination center has the highest specificity of 99.8%. We have a multidisciplinary team, MDT, find that 51% of the false positives were actually peripancreatic diseases, such as dilated common bile duct or other types of tumors detected, which is very close to the pancreas region. We have adjusted specificity, taking these findings into account. We have 99.9 for PDAC identification. So the other question is, can Panda change the standard of care diagnosis? We have a case study here. When these patients come into the hospital, this patient underwent a chest CT just for lung nodule screening, routine screening, but there was no pancreatic lesion reported at that time in that chest CT. And 7 months later, when we did this study, we collect this patient. Then Panda find a 95% of non-PDAC lesion here. After review by our team, the doctors decided to recall this patient after 7 months. Okay, and the patient come back to the hospital and did a MRI for follow-up examination. And the patient, the MD recommend for surgery after consent of patient. We find that this is actually another type of rare pancreatic cancer, PNET here. Actually, if the Panda in this case, Panda actually changed the SOC diagnosis. We recall that patient and did a surgery. Okay. In the real world study, this is only one example. We have 26 pancreatic lesions that were not detected by the initial standard of care, including 1 PDAC, 1 PNET, 3 IPMs, 1 metastatic cancer, 6 cases of pancreatitis, and 1 peripancreatic tumor, and 13 SCNR cysts. This is benign cysts. So in this initial findings, we can see that the opportunity screening with Panda can advance the early detection of pancreatic cancer malignancies and high-risk lesions. For the safety and efficiency issues, we find that only 0.5% of patients had false positive AI findings, and 92 of them were easy to roll off by the radiologists. Of the false negatives, which are missed by the Panda, 89 were benign cysts, which is 25 cases. Most of them, 19 cases, were less than 10 millimeter in diameter, which means basically patients are fine with this benign cyst. The remaining 3 consisted of PNET, a case of chronic pancreatitis, and a lesion of undetermined type. Then I want to introduce the model evolution, which we want to iterate the model to make the model become stronger. After the real world study, we collect the false positive and false negatives, and we add a new class, acute pancreatitis, which we think it is crucial for real world deployment. The resulting model, we name it Panda Plus here. In summary, Panda Plus has a very high sensitivity, over 95% of early stage PDAC detection, and was evolved to achieve higher specificity. First, the specificity is not 99.9% in real world consecutive patients. We first see like 99%. Now we train with the false positive. We iterate this model. Then this model can achieve 99.9% specificity, which means 1 false positive in 1,000 patients. We think this is very good for screening scenario here. And this model was also evolved to have 90% sensitivity on the new class acute pancreatitis. And this model, as previously evaluated in the reader studies, this model also exceeds the upper bound of human expert radiologists. and also can detect misdetections of standard diagnosis, which are initially missed by the radiologist, basically small tumors or the tumors unrelated to the purpose of the examinations, which is called opportunistic screening. And this model can also detect malignancies at the surgically resectable stage, sorry. Okay, I guess this is end of the presentation. So we will go over the questions, or we first go through the talk by Jiawen.
Yeah, thank you. We do have just a couple quick questions that are very related to some of your last slides. So maybe I can just go through them very quickly, and then we can hop over to our next talk.
Okay, sure.
So two questions. One is early stage PDAC can significantly help patient survival. How accurate is PANDA for detecting different stages of PDAC? And what about hyperplasia before the cancerous transformation? I'll let you answer that one first before I hop to the second question.
Okay, yeah. Thanks for the question. This is a very great question. I actually have a diagram here. It's very small here. Here, probably we all missed that. This is the portion of PDAC detected by PANDA, in which we can see in different stages. This is the T stage. T stage is radiology stage, which means for T1 is less than 2 centimeters in diameter. And stage 1 cancer, this is commonly used TNM stage here. We see that for both internally and externally, we have about 96% sensitivity for stage 1 cancer. And for the T1 stage, we have 86 sensitivity internally and 92% sensitivity externally.
Okay, cool. Thank you. And then the second question is, how are the multi-center collaborations established and agreed upon, like the logistics? And is there any mechanism of incentivization? This could be a bottleneck for real-world problem solving compared to data analytics. So yeah, basically, how did you collaborate with the sites to be able to deploy this in clinical practice?
Oh, yes. For the multi-center collaboration, we're basically using the data here. We have the doctors, the related doctors in different multi-center evolved in this project, which we have their names on the academic paper here. And all the data is approved by the responsible IRB here. So there's no issue for the data. Yes. And
Okay, cool. And then both me and Gao Hong had some questions about the real world applications. My question is a little bit more upstream of you mentioned that when people get CTs, like they could get it for routine like lung nodule detection, you said. I was just wondering how often do people, because there are like allergic reactions and certain risks to getting CTs, like how often do people get this in general as part of their preventative routine, such as like preventative as in like you just go in and do it annually? And what's the opportunity there for this to like what was the interest for people to get pancreatic cancer screening on a more routine basis? And Gahon had a question about like how far would Panda be ready for commercial use? So similar.
oh yeah. So for the commercial part, for the commercial, it's not the it's not the purpose of this talk. But as mentioned by Dr. Lu before, we still have API on the cloud basis and has served hundreds of thousands of patients here. Basically, is we can whenever you have a screening CT of whatever purposes, you can use our API to use Panda. Yeah.
So maybe I can chip in to answer these two questions.
Okay.
So first of all, there should be generally speaking like a risk model for general population. Like age is one of the most important risk factor for cancer and other chronic disease. It could be some other like a simple non-imaging like a biomarkers depends on the general health condition or index for the population. Generally speaking, you know, I would say, there are two purposes. One is really for dedicated screening purpose. The other is for incidental findings. So we do have a lot of incidental findings because we have CT exams for whatever reason, may not be cancer screening. But since the data is already in there, it's very common in clinical practice, you will find incidental findings, sometimes very important incidental findings. So I'll give you one example. We right now we offer incidental findings for many of the cloud-based PACS companies, and we just found 17 new patients they have PDAC. That has been confirmed by the CT AI algorithm as the first reader, and then it has been confirmed by our collaborators, by our clinical doctors. So this patient has been recalled. We haven't know the final result yet, because this screening was really not for confirmation. Even typically it can be confirmed, but the current protocol is recall the patient back and ask them to do contrast MRI or contrast CT to have a confirmation. Then if they're eligible for surgery or biopsy, they will do that, right? So so generally speaking, right now we are most targeted for incidental findings, especially for esophageal cancer screening. But in the future, it could be a dedicated risk model, like a non-imaging risk model, to profile subpopulations. We can recommend them to do maybe a CT exam like annually or every 2 years, and also to maximize the benefits of the CT exam is you don't just do one cancer screening, but you do a pan-cancer screening. You don't just do pancreatic cancer and esophageal cancer. You maybe do 8, 10 type of different cancers and other chronic disease profiling, like liver steatosis, liver fibrosis, all these kind of like a pre-cancer important clinical biomarkers. Um, that we see that will be the future, and we are building that future step by step. We're not there yet. For the commercial part, right now we are applying like a level 3 license in China and probably in Japan as well, but it takes years. Right now we are also building Panda 2. So right now you have Panda and Panda Plus. We're going to have Panda 2, which is supposed to be work even better. I think we're not urged to apply lessons for commercialization. We're mostly focusing on really get a very, very good clinical result. The license does not mean commercially you will be successful. I think to validate our model again and again in all different kind of scenarios, in real world scenario, make sure it's really work, really helpful. I think that's very important to be responsible for our ongoing development. And also we keep like a transparency. We basically publish whenever we can and keep open science in that sense. I hope I answer your question in this way.
Yeah, no, absolutely. I think if it is integrated into more preventative routine practice with a patient like risk model type of format, then it would be extremely life-saving. Like we're already starting to see the impacts now. And I'm sure there's similar questions on this for the esophageal cancer screening talk as well. But for the sake of time, let's move forward to Dr. Jiawen Yao's talk on esophageal cancer.
Okay, let me show my screen.
Cool, we can see it.
Okay, cool. So hi everyone. Thanks Dashu and Dr. Lulu for giving me this chance to share our work on esophageal cancer. And I'm Jiawen from Dharma Academy, and from Yingda's talk, you can see what we have done on pancreatic cancer by using the non-contrast CT. So I will show what we have done on esophageal cancer screening. So here are some background, and globally, esophageal cancer, and the short as EC, was the seventh most common cancer and the sixth leading cause of cancer-related deaths in 2020. And there is one type of esophageal cancer, like the esophageal squamous cell carcinoma. Actually, half of the such squamous cell cancer happen in China. So the EC has a 5-year survival rate of less than 30% because patients are usually diagnosed at advanced stages, and the signs and symptoms tend to be latent and not specific. So early stage EC is associated with a higher survival rate, like the 5-year survival rate of 80 to 90%. So early detection of the EC is very important, and this will have a great potential to reduce mortality. The early detection is very important. Unfortunately, there are no guideline recommended screening tests for EC in the general population. And here are some popular screening tools, including the blood test and the endoscopy procedure. So for blood test, it can be used to detect multiple types of cancer. It's easy to apply in the general population, but according to the recent study, we can see it's not very sensitive for early stage EC. And a well-established screening tool is the endoscopy procedure, which has shown very high sensitivity in finding the early stage EC. However, it's a kind of invasive and resource intensive method, so it's difficult to apply to the general population. And compared with the endoscopy, and also we have seen from the PANDA in that I introduced before. So non-contrast CT is a non-invasive with low cost. So routine CT exam offer opportunistic screening at no extra cost. So more importantly, it can be easily applied to the general population. But it's not easy for human eyes to detect the esophageal cancer. So how about AI? Is that possible to detect the esophageal cancer on non-contrast CT, just like PANDA to detect pancreatic cancer? So we actually follow the similar from PANDA. And first, we need to build a data set that has a ground truth mask on non-contrast CT. So in this study, we invite the experts first label masks on contrast enhanced CT according to the clinical records, like the surgery or the endoscopy reports. So then the mask on contrast CT will be transferred on non-contrast CT using a robust image registration method. So our algorithm actually is built up on the segmentation model. And in the segmentation, we try a position-sensitive full attention layer in each encoder to model the long-range dependencies in 3D CT scans. So this could help further boost the performance. And we also conduct a reader study for human and AI comparison. And the main results include the first, we found that our model could outperform the mean doctors. Like we have a high sensitivity and specificity, and also compare with other tools, and we could see we can detect more early stage cancer, and also we can detect the benign tumor. So in this study, we collect almost 750 patients, and include 481 cancer and benign tumor, and also the 260 normal controls. And to train the model, we used the 161 patients, which had the 300 cancer, 57 benign tumor and 180 normal. So we built another 180 patients on the test set, including 80 cancer, 20 benign tumor, and 80 normal controls. And we also invite 4 readers to read the testing set. And there are 2 radiation oncologists and 2 radiologists. And we compare the 2 types of baselines. So the first one is the very famous segmentation model, Unite, and the second one is the one detection-based method, the lens. So these slides show the ROC curve of our model. And in this task, we actually define as a 2-class classification, cancer and benign as a lesion versus the normal. And we can see in this setting, our model has a AUC of 0.90, almost 0.99. And the 4 readers, actually the mean readers had the performance sensitivity 75% and specificity 84%. And we can see that the readers with more years of experience will detect more easily. And the best radiologist has sensitivity 77% and with the specificity 95%. And in this slide, we show our model could have significantly higher AUC than baseline models, including the Unite and the lens. And in the reader study, we found that the radiologist 2 who has a better sensitivity, almost 80% sensitivity, and in the 3-class task, like we classify the cancer benign and normal. In this task, radiologist 2 had achieved the accuracy of 75%, 45%, and 81% for each class, respectively. And our model performs much better than the mean doctors by the margins of 17%, 31%, and 40% for cancer, benign, and normal, respectively. We also report the patient level and tumor level detection results across the benign tumor and the each T stage of esophageal cancer. Tumor level detection means how segmented masks overlap with the ground truth mask. And if the size is larger than 0.1, we believe it's like a correct detection. And if not, it's considered as a misdetection. And the patient level just if we believe it's a cancer and it will be the ground truth label is cancer, so it's correct. It's will not consider the segmentation mask. So from this table, we could see our model actually performs better in detecting the benign tumor and also the T2 stage. And for advanced stages like T3 and T4, we have the similar performance with the Unite baseline model. And yeah, but from the tumor level detection, we could see we have the actually much higher detection rate than the Unite. And we also found it's better than the radiologist 2. Compared with the state-of-the-art the blood test screening at this specificity level, we can see our model achieves much better results in detecting early stage esophageal cancer. Like in stage 1, we have the 34% versus the 13%. And in stage 2, it's 94% versus 65%. And moreover, our method can detect the benign tumors, but the blood test cannot do that. And in another experiment, we compare the model with the state-of-the-art endoscopy AI system, which was trained on 15,000 patients with full supervision. And in this setting, it's a little different because they will believe the cancer, their goal is to screen cancer. So the benign tumor will be considered as the non-cancer. So the benign and the normal will be the normal controls will be the negative. So in this setting, we report our results again, and we could see our sensitivity now is 91%, and this endoscopic AI model is 94%, but we have a little higher specificity, about 93%, and from these results, maybe it's comparable with such AI-driven endoscopy too, but our actually is more flexibility because we built model on non-contrast CT. So here we show two cases, and one cancer and one benign tumor. So in this case, we could see our model could segment this stage 2 cancer, and and also the benign tumor as the baseline in that model. And actually, those two cases were missed by the readers in the reader study. So in the conclusion, we investigate a relatively convenient and simple opportunistic screening solution of esophageal cancer, and to better capture the global context, and we use a self-attention layer in the encoder block, and we could see our model could detect the EC on non-contrast CT and achieve high sensitivity and the specificity, and outperforms the mean doctors by large margins. So we have shown that the good facility of using non-contrast CT scans as a promising clinical tool for the potential large-scale EC opportunistic screening with no extra cost. Here, this algorithm actually has been implemented in our more intelligent medical imaging system, and it could be easily deployed in any hospitals if they want to try this feature. And it takes the non-contrast CT and inputs, and the algorithm will segment the mask and also give the abnormal probability. So if the doctors review results and refer patients if the further endoscopy procedure needed, and we know early detection of EC is especially crucial for the best possible outcome. Here is the full window of our DAMO IMI system, and the doctor could view results here, and also will show the masks and some statistics about segmentation results, and also the probability. And this is actually the normal patients. And also our API available on Alibaba Cloud, so everyone interested in this work could try. And but unfortunately, right now the documents is written in Chinese, so maybe in the future we could revise it and translate it to English and provide such English version. And also we can deploy the system in the hospitals. And right now, those are three cases that from retrospective study. So doctors found that our model could help them detect those three cases because some actually are difficult for them to find on the non-contrast CT. So currently this project is still in progress because we need more validations, we need to get more clinical results, but hopefully we wish this model could provide its values in the large scale esophageal cancer screening. So that's what I want to share with you today. And thanks for listening.
Well, thank you so much, Jiawen and Yingda, for your talks. These are really, really important topics in preventative diagnostics, and especially for cancers that are so hard to detect and treat. So it was really, really interesting to be able to see was the cutting edge research in this field nowadays. So yeah, thank you for your time and for your talk. I know that there's a lot of technical questions that are already addressed in the chat. Maybe just one last question before we go from Jingye, who says, great talk and thank you for your efforts in delivering a presentation. I would like to highlight a consideration regarding the study. Unlike the previous research, there appears to be an imbalance in a number of patients in the study, which could potentially lead to a biased assessment of the model's performance based on the ROC curve. In addition to the ROC curve, any other methods can be used to evaluate the performance. For example, how's your model's performance on the precision recall curve? So I think that was a question directed towards Jiawen's presentation, if you could just address that.
Yeah.
Also, Jingye,
Yeah,
if you
that's
want to
a good question.
more detail on what do you mean by the imbalance in the number of patients?
Yeah,
let's
see.
I think Jiawen, this work may not may not directly address the from this population. It's not a screening population. We do have like a this work was published last year, so Jiawen does have like a new result. It has not been published, so it has not been really discussed here. But imbalanced population is a natural um, question for cancer screening. You have like more than 99% of patients they are non-cancer. In that sense, sometimes it depends on your risk model. You could have much higher prevalence about cancer in terms of every 100,000 people, right? But in general, generally speaking, it's about um, uh, two metrics. Most important, first is the sensitivity, the recall under different T stages, right? Even sometimes maybe T0 means like pre-cancer. The other number is actually important is the precision. The precision, why precision is important is you do not want your precision to be lower, to be very low, like 10%. The precision means 10, even precision 10% means like every 10 positive patient you detect, only one of them are really positive, right? And under such a circumstance, the physician will less trust the AI tool or whatever tool it is, and also it can cause waste on anxiety, unnecessary patient. Our goal is about 50% for the precision, and we try to get the sensitivity as high as possible. So in general speaking, this is our protocol for all the screening tools we're building. So around 50% precision means every two detections, one of them are really positive, and sometimes the positives are very easy for physicians and radiologists to or other like specialists to rule out. For the pancreatic cancer, the example is same for the all the cancer detections. So basically, we need to get a precision under control, and also we need to get precision under management. So this is really built in. I think the work Jiawen show you here was published last year. It's not the newest work. We have more evaluation on thousand of patient, which has more more natural the statistics. Yeah, as the same. The first work is more clinical. It has the real world study was the continuous patient population. So that's more naturally occurring the population. So that's the highly imbalanced problem. And yes, so we don't really have a precision recall curve, but we you know, typically you get a cutoff point from AOC curve, and to balance out the recall and precision. Yeah. So precision is very important. Yes, indeed.
Yeah,
Thank
thanks
you,
for
thank you for your explanation. I can further explain my questions. So for ROC curve, which evaluate the false positive rate, but when the number of actual negatives is very large, so even a large number of false positive will also lead to a small false positive rate, and they will also lead to a very high AUC, but it does not evaluate the actual reality of the model. But after you showing your data distribution, you have more cases than the normal control, so you might not have this problem. And thank you so much for your explanation here.
Yeah, thank you guys for all of your questions. And I think a general theme that I got from all of these talks is that beyond just the algorithmic excellence here, there are a lot of considerations and interest in implementation in the real world. It goes from a spectrum of, okay, first, either we want to identify the high-risk patients and put a lot of effort in that and really drill down to the patients who need the screening. On the other end of it is just screening as many people as possible to find either opportunistically or preventatively what diseases that they are likely to have so that they can go ahead and get any treatment that they otherwise might not get. And on one end, it's a lot of algorithmic considerations and then a lot of data science work to be done. And then on that second other end, there could be this concern of medical waste as well. So I love that beyond just the algorithmic considerations, you guys are considering also the clinical background and the possible implementation of all these algorithms. And this seems like a really good first step in the right direction. So thank you again, Dr. Lilu, Yingda, and Jiawen for all of your talks. Thank you for all the participants for making this an engaging conversation for everyone. And I think we'll end our talk here today. Looking forward to our next month's presenters as well.